Hello everyone. So today I'm reviewing PR 32993 right here. So this is the issue tab of this PR, and so this will give you the brief summary of what this PR do and what it aims for, and we'll talk about this at the end of the session. First, let's open this on the Bitcoin repo. So this is the original PR listed here, and it was a fuzzing related PR. So what it does, it adds a fuzz target on wallet transaction scanning. So the function name is, or the method name is scan for wallet transactions. So in this PR, he implemented first target for this function. So we'll see how all of these logic works are related to each other and how fuzzing generally works with some first target. So the change is not very big, means in terms of the lines change. So there is only a single file introduced here. But yeah, this can give you the general idea about fuzzing in Bitcoin and how fuzzing and how writing a target for some method can work together. So it's a good test to understand all of these things. So first of all, as you can see, uh, it introduced a file called scan.c++ or CPP, and it's generally a fuzz test. So I will open this my coding editor to explain you better here. Okay, now I think so. It's under fuzz and in the source and fuzz, and you will find this if you go to the uh, author's forked version of Bitcoin. Let's understand what this test trying to do and what all the things are going here. So first of all, this test was written to check a wallet feature. The feature is related to scanning a blockchain, a whole blockchain. A blockchain means a chain which consists the number of blocks in them, and then it's related to wallet means it specifically tries to find a specific information around the blockchain which relevant to that particular wallet. So we only need to find some information from the huge amount of data out there in the blockchain. We just need to look for certain transactions uh, which might uh, similar or related to our wallet. So as I said, this this method scan for a wallet transaction. So what it does, scan for wallet transaction, what it does. So simply it scans for the whole blockchain and find out the transaction. Uh, in transaction, it finds out inputs and outputs, and if those inputs or outputs uh, will change the result or will they affect our wallet state in some way. So it tracks all of that thing and then update the wallet state at the end. So After running this function, your wallet will up to date with the current block tip, the blockchain tip. So this is very necessary and important function for any wallet we have because uh, it keeps tracks of new transactions, new new inputs or outputs you send or you receive from someone, and and then adding all the things together uh, and showing you the result at the end. So for this test, what it does, first of all, we are initializing a global variable, a pointer uh, of testing setup type. What testing setup is? It's a small active node which consists many things inside. So it contains a valid chain params and chain state and all the things related to wallet. So it's a small, fully functional node, you can say. So there is a function called initialize here. So this function uh, called when we run our first target, and I will show you where we invoke our first target and how this calls this initialize and all. So inside initialize, what we are doing. So we are creating a testing setup of type const and static. So this is very important. So static, why we are choosing static? Because this is a first test. And if you know, a first test runs a millions or thousands of times. So, and creating the testing setup can maybe expensive in terms of performance and resources. So we don't need to want to call this initialize like millions of times after each iteration. We don't want to do this. So this initialize calls only once, and because this is static, it will only runs once, and afterwards, so if you call this function, this will return the previous value. It will not recompute the things for you. So it will only work, only loads things once at a time, not more than that. So after this, we are setting a global G setup variable here, a variable, or you can say a pointer. Which is getting the instance of this by dot get. So it's a pointer, a unique pointer. So using this G setup, we can like take the reference of this testing setup and do what we want to do in later on. So this is the key here, and now a G setup contains all the things we need, and then this is a function called remove and create does, which represents for directories. And what it does, it does some cleanups. For example, this will first get the blocked directory path from the global variable we created above. As you can see, this is the global variable we created. After from this, we are fetching the block directory path, and then we are also fetching some blocks and index the path of those. And after fetching all the paths, we are removing all the contents in them, like all the contents, including the directory. We are deleting all the things. So we are starting with a new fresh state. Okay, and then here we are recreating them. And so we remove all the things before, and now we creating this again. That means these directories are empty and there is nothing inside them. So we can start with the fresh state. So this is important because this function is important because as I said, fuzzer runs many times, many iterations, thousands or millions of iterations. So what if we don't clean those files, then we can mess up with everything. So we need to start with a new state every in each iteration we have. So here is the first target. So when this file when you run this target, this function will run first. So this is the entry point of this file. Our first target is the entry point of this file with the name a wallet scan. So this is the name of this first target, a wallet scan, and it also takes the second parameter, which is the initialize. So what initialize does? It calls the initialize function and do all the things written inside that function. For example, and it will like this this runs only once. So according to the nature of first target, the initialize runs only once, not every time. So it calls only once. For example, here our .init represents initialize, which is here, the function we created here. This gets called, and as you can see, this do all of the things I just stated. Uh, and once, yeah. So after entering in the first target, so the first thing we do is just creating some random seeds for deterministic behavior with zeros, and then the first data provider gives us some random data. So the data we fetch the data from buffer and the size of the data into this first data provider variable of type first data provider. So after this, uh, so we have data, we have first data here. Sorry, I'm sorry. I don't know what happened. Oh, no, never mind. I don't know what happened. It's just okay. So let's get back into the topic. So now, first we call this first target. Afterwards, we have some random data in our hands, and then we call this function remove and create dirs, which I just explained. It cleans all the directories. So now we have a fresh state. After having that fresh state, we are resetting the chain man. So this cleans all the blockchain data from the memory. These two things clears all the data from the memory and all the data in terms of all the chain data, I'm saying all the chain data from memory. So after we have a clean chain state, we load and verify active chain state layer. Like we have an active chain state, uh, which doesn't hold any data inside. And then, yeah, and then we check whether with some validation signals. And after all of these things, there is an if uh, condition. So this if works on randomness, deterministic randomness, because this provides this random behavior, but deterministic in the sense of this will return true or false. Anyone. So uh, a true will be written or a false will be written, but yeah, not any other value like 0, 1, or something, any other value. So yeah, this is the expected behavior, and this is the deterministic behavior of this consumable. So so suppose if this returns true, means we entered in this condition, and then what it does, it will just simply enables the block filter. It enables block filter, and after enabling the block filter, so what is block filter? So I just uh, I will just explain you briefly, very briefly, about block filter in Bitcoin. So just a block filter is nothing but uh, it uh, it contains some information on your hard disk. So the information about blockchain data, but it does not contain whole blockchain data. Means all the transactions and then the witnesses and all the other things included in the transaction. It only contains a very limited amount of data in them. Meaning it only includes script sage and then some inputs and outputs. And it also doesn't contain any OP return because we don't need the OP returns. It's useless to store in block filter because we only need to know about very few and important things. So we just uh, randomly allow this filter to be active here. So based on this consumable, which is random, this will allow the block filter to on or off. For example, if it's true, then the block filter will be enabled in the future run of this code. So this effort simply just check if we have block filter index enabled or not. Yeah, because we enabled this here, and if it is enabled, then okay, the effort passes and nothing fails or nothing will break here. And then same randomly, as you can see, there is also consumable here. So again, randomly we destroy this filter indexes. It's a random choice. It's this why this is here, like why this condition is here, because we this is the first test, and we need to behave very differently. We don't need to follow some strict patterns. We need to test things in a little different way than it works. So that's why the first test finds some hidden bugs in programs because of this nature of complexity and the nature how they work. So this is totally different from any other test. That's why first tests are very different from other tests like functional or unit tests. So it decides randomly about to destroy the block filter. So basically, we are just checking here. First, we are randomly enabling the filter and then randomly disabling the filter. And then we will proceed with the further code. So uh, if there was a bug in program, suppose, then something might uh, break later on. So if we found that bug in our code, that's a good thing. So here we are just creating a instance of a wallet, and uh, like the name of the wallet is this first wallet A, and then this is the extended private key. Why we are hard coding this? Because we want a uh, deterministic behavior in terms of we want to reproduce things recover the further private keys and public keys. So our fuzzer. So it doesn't matter how many times our fuzzer runs, but yeah, the keys generated can be the same every time. So we can recover from the failure state if this will happen. Suppose if code breaks, then we can debug the code in more uh, with more flexibility. So using these private keys or extended private keys. So this is a reservoir uh, object of type wallet risk and reservoir. So what this does, reservoir is simply used by the scan for wallet transactions. So how this happens? Like when scan for wallet transaction uh, called, uh, first it will check whether uh, whether reservoir returns true or false. Like this will calls wallet risk and reservoir, and then according to this, suppose if reservoir dot reserves gives you true, then the scan for wallet transaction proceeds with scanning. Otherwise, not. If reservoir dot reserve returns false, then this will fail. This will not run. So this function, scan for wallet transaction, depends on this reservoir here. So what we are doing here, we are making this true every time. So our function here will run all the time, no matter what. So here we are just setting the reservoir time between 0 to 1000 seconds in the future. Well, this is the fake time. So we are just enabling this by default. And so this is the main part of this first test here. First of all, we are declaring a bool variable which initialized with a true initially. So this represents the good data. So the data here is the data here refers to the further data we have. This one, first data provider. This is our data we are targeting. So initially it's true. So so there is a limited while. So limited while is a while loop, but it's a custom version of while loop in Bitcoin. So it runs with some conditions. Um, for example, uh, this is true, and if first data provider dot consumable here here also this is purely random. So for example, this will return true or false randomly. But the maximum time this loop can go or run is 20 here. Okay. So no matter what this will return in on each iteration, this will just run 20 times. So at max, we can have a chain at max 20 blocks long. So after inside this loop, we are just creating an block assembler options. So some options we can uh, assign to blocks. First of all, we are disabling the test block validity, means we are disabling some extra test because our process new block function will do all these checks later on. So because of performance, because to reduce the time of further, we are just disabling those tests here. And uh, here again, this is a random condition. A random if condition means if this is true, which again based on true randomness. If this is true, what this will do? Uh, this will take out the Coinbase transaction, the output of the Coinbase transaction, and just rewrite with our wallet address. So first wallet is what we created here. This is our first wallet, and we are just mm, appending or just removing the existing Coinbase output script and then adding our uh, address which corresponds to our wallet. Why we are doing this? Because because we want this test this function to run, and what this do? So this will check for the transaction which is relevant to our wallet. Okay, so if there was some transactions which are dependent on our wallet, for example, here, suppose we replace the default Coinbase output with our wallet address, so it means that this function will find something for us. This will not just return nothing or empty or any other thing. So this will work. So this will find, yeah, that the transaction in some block is related to our wallet. So that's why we are just replacing the Coinbase with our wallet address, and then after, and it's randomly, as you know, this can happen or cannot. Like there is a maybe term in this. And there was a here we are creating a block template here, and this will create a new block with the options we initialized above with all those options. We are creating a block template. This is the basic block template, and it includes a valid block header and a single Coinbase transaction. That's why if you see this asset, that means a block has only one transaction. The transaction count is only one, and that is our Coinbase transaction we have. We don't have any other transaction rather than the Coinbase transaction. That's why this asset will pass without any error. So, okay. So there was another inner while loop, limited while loop. This is bounded by 20, means the max iteration of this loop is 20, and and the minimum can be 0, I guess, yeah, and the maximum can be 20, and this also works on this random variable. So what it does, so this inner while loop creates transactions, at most 20 transactions or at least no transactions. So this creates a transaction. So how this will create transaction? So uh, so as I already said, like our fuzzer provide us some random data in first data provider. So using that bytes of data, we are just creating a transaction instance. So, and we are saying, yeah, we need witness transaction. So we need a transaction with witness. So this is specifying that. And uh, after, so the first data provider here can be any random data, any random values you can think of. So it contains any bytes or any sequence of data. Yeah, so generally the data was generated by fuzzer, so the fuzzer can create any type of data. So using that data, just creating a transaction, and then we're trying to deserialize that transaction. Why? Because we want to check whether the transaction we created from this data is valid or not. Because you can't create a valid transaction from any sequence of data. You need some sequence of bytes in some order or in some manner which follows some rule to make a uh, transaction. So if we deserialize a transaction with a very bad structure of data, generally it will fail. So in the next step, what we are doing, we are just checking this. If the deserialization failed, then we are just toggling this good data flag here to false. As you can see, we just initialized this with true, and now we are just turning this into false, and then we are returning early. We don't want to proceed further. If we have a, a very bad transaction, or if we don't have a transaction, if we failed the deserialization, then we just simply return early in our code. We don't process further. The another loop will run, and then suppose the data is not means it contains some transaction and it has some output. Means yeah, the transaction is valid. Now, if the transaction is valid, now based on randomness, what this will do, this will just create a script pub key and then replace those script pub key with our wallet pub key. You can say, yeah. So our wallet will create a pub key with respect to this random data and which is valid according to our wallet. So our wallet will recognize this pub key generated with the same data again. So we are just doing this because we want to work this scan for wallet transaction function to work, and this function will return all those things which is related to our wallet. So if this transaction contains some output which contains an address or a pub key which is generated from our wallet, so this function will work, and this will find something for us, and this will further explore uh, some parts, some edges of the code base. Means the code will penetrate deep uh, into the conditions in the code. The path can be explored further if we go with some valid structure and data. So that's our goal here. So after this, and this is also based on randomness. This may happen or may not happen. So it's on randomness. And afterward, we are pushing that transaction on in our block. And after that, we are regenerating commitments because we created some transactions, and those transactions contain some witness, and we need to recalculate the witness commitment to make our final block valid. So that's a very important part for us to regenerate the commitment. So the final block is valid. So after this, we are processing that block. So we are passing our block to this function. This will process the block, check all the things are valid according to the Bitcoin rules, consensus rules, and if it returns true, then we can get the height of the new block, and then we are locking the our first wallet, and we are just calling this method which just uh, what this does like this says, yeah, there was a new block mined with some new height, uh, and then with some uh, block hash, which is new. So let's process according to this. So this will process the new block, maybe append to the last created block, and yeah, afterwards we are just initializing the start block time with the genesis block hash, uh, which is uh, which is the block zero. So because this is valid start block, uh, because any chain can contains a genesis block, so this is always valid. And afterwards, the uh, like basically on the true randomness, uh, we are we are overriding this start block with some random integer, which which may be invalid or which uh, may be valid or which is just absolutely garbage value. You can't know. Well, it's a valid because this is consuming the U into 256 type. So yeah, this will not to give you the garbage value. This will give you the actual value within this variable bound. So yeah, but yeah, so the value you got the start block. Suppose you have a blockchain of 520 and you got the value here, suppose 400. Then still the value is correct according to this variable type. But for our use case or for our blockchain, the value is not correct. And then the start height is also choose randomly, and then max height is also choose randomly. And then we are just about the rescan also randomly. And after all of these things, we call this function scan for wallet transactions. And then we pass the start block, start height, and max height, all of these things. And then first data provider, and yeah. So after all of these things, this function will run, and then uh, this will run, and if there was no problem in the code, this will return as expected. And if there was any problem, the function may return some error or a stack fault or any other memory related errors if there was some bug exist. Otherwise, this function will run perfectly without any problem. And the return type of this function is void because we don't need any data returned by this function. We just only care about whether this function is successful or not. So that's how this whole function tested using first target. And yeah, it simply just creates some blockchain of size at max 20, um, and then uh, replace the Coinbase output with our wallet script, and then create some transactions which is bounded by 20 at max. Uh, so after creating some transactions, this will regenerate the commitments, and after commitments, this will just generate a new block. And after all of these, we are just initializing some start height or max height, which may or may not be valid according to our use case. But we want to test this function for invalid values. That's why mm, we are just providing any value here. We don't care about if this is greater than the current blockchain size, which is the 20. So yeah, we need to provide some unexpected values to this function, and that's how all the first test works this way. So yeah, that's all uh, for this test. For this first test, let's get back to the question. Uh, so we have a few questions. Uh, okay, so the first question is, what's the difference between the harness and the first target? So the so simply, if you see here, so this is the target. So the first target is the starting point, and it defines the starting point and the function you need to call. So this is the first target, and the harness is the this function. Our harness is this function, scan for wallet transaction. So this is the so the thing we need to test. We need to first is our harness and the starting point mm, of that test is our first target. And so the second and third question is a little bit logical and needs some thinking. But yeah, so the limited while loop for generating blocks and transactions are both capped at 20. How was this number chosen? It is a balance between test coverage and performance. So yeah, this question is uh, can be discussed and yeah, I in my opinion, yeah. So it capped with the 20, and I don't think there was any specific reason for this. We can also, I think, increase the size a little bit, and this will not create any problem for us. And yeah, but yeah, the one thing is if you increase this number with very large numbers, this will create some performance issues for us because, for example, if you cap just to 1,000, then in each run, in each target run, you are creating at max 1,000 blockchain blocks. You are creating 1,000 blocks every time in each run. And suppose this function runs 10,000 times, then what will happen? In like the upper bound will go exponential. So this is very bad complexity, and this will absolutely slow our program exponentially. This is not the good way. I think that's why the PR author capped this at 20. So the next question is the test uses a hard-coded descriptor string and sets safe progress to false. Would it be beneficial to fuzz these as well? For instance, using different key types or testing the progress saving logic. So I think uh, because as I already told you, so the reason why there is a fixed private key because we want some determinism. Suppose if first just find some bug, but after finding that bug, we need to know how this bug triggered. So we need some determinism uh, in our first target run. So this gives us the determinism because we can create the same private keys or same public keys using this extended private key, and we can debug more about the error. And yeah, and with related to progress paving, I think so. We blocked the we blocked the progress saving somewhere in the code. I need to see. Yeah, for example, here you can see this will not create any log file, meaning in on every run, this will not create any log file. And This is good in terms of resources because we don't want to log everything because the first target are very uh, aggressive in nature in terms of executions per second. So we don't want to bloat our hardware, mm, like our storage with some log files. So yeah, so progress saving logic needs to be like off for a reason, for the performance reason mainly. And about uh, like to first these save progress and these descriptors, uh, this can be done in another first test, but not this one. Yeah, because this first test only covers this, and it's a good practice. We can fuzz these hard-coded things, but I think we should not try to do uh, in this file. So I think that's all for today's lecture, and yeah, that's what I need to share with you about this PR. Thank you.